At 21:39 on the evening of October 19th, 1989, an alarm screamed inside the control room of Vandellòs, the Ford nuclear power station. Turbogenerator number 2 was vibrating. Abnormally, the reactor sat on Spain's Mediterranean coast in Tarragona. 480 megawatts of electrical power. A French-designed gas-cooled reactor using natural uranium and graphite moderation. One of only 9 nuclear reactors operating in Spain at the time, and in exactly 60 seconds it would be on fire. The operators had no idea that the next 4 hours would become Spain's most serious nuclear incident ever recorded, or that the cascading failures about to unfold would push the facility to the edge of catastrophic loss of cooling. What began as a mechanical vibration would ignite a fire fueled by hydrogen and lubricating oil. That fire would knock out electrical systems. Those electrical failures would cripple pumps, and without pumps, thousands of cubic meters of seawater would flood the reactor cavity. All while the reactor's carbon dioxide coolant climbed toward pressures that could rupture safety barriers. This is the story of Vandellòs, the first Spain's forgotten nuclear fire, and the reactor that nearly lost control. Before we dive in, please consider dropping a like and subscribing. At 21:40, the fire ignited. Multiple explosions erupted near turbo alternator number 2. The control room immediately initiated a manual reactor trip, shutting down the nuclear reaction. But shutting down a reactor doesn't mean it stops producing heat. Decay heat continues, and that heat must be removed continuously, or the fuel begins to overheat. Vandellòs I was a unique design in Spain. A UNGG reactor, uranium natural graphite gas-cooled, graphite-moderated, the only one of its kind in the country. It used pressurized carbon dioxide gas to carry heat away from the uranium fuel. That CO2 circulated through massive blowers, through heat exchangers, back into the reactor core, a closed loop that depended entirely on electrical power and mechanical integrity. And now, both were failing. The source of the fire was brutally simple. A lubricating oil line had ruptured at alternator number 2. Oil sprayed into the turbine hall. At the same time, hydrogen, used to cool the alternator windings, began leaking. Hydrogen is invisible, odorless, and explosively flammable. When it mixed with the atomized oil and ignited, the fire spread with terrifying speed. Flames consumed cable trays, insulation melted, and the explosions kept coming. Witnesses described a roar, then flashes, then thick black smoke filling the conventional island, the non-nuclear side of the plant. But the fire didn't respect that boundary, because the cables it was destroying carried control power to the reactor side. At 21:40, within seconds of the fire starting, the plant began losing its 48-volt direct current control power. This wasn't the main electrical supply, it was the control system, the nervous system of the plant. And it was dying. Without 48 volts, pumps couldn't be controlled, valves couldn't be operated, alarms couldn't function properly. At 21:43, control power to the EDOR system, demineralized water storage tanks, was lost. At 21:46, sump pump controls went dark. That meant the plant could no longer automatically remove water accumulating in low-lying areas, and water was about to become a very serious problem. Meanwhile, the carbon dioxide cooling system was collapsing. Vandellòs I used 4 massive CO2 blowers to circulate coolant through the reactor. At 21:40, as the fire erupted, these blowers were commanded to a fixed speed, 400 revolutions per minute, manual control only. The automatic regulation system was already compromised. At 21:47, blower number 4 tripped, lubrication failure. 1 minute later, at 21:48, it lost tightness. CO2 began leaking into the plant. At 21:49, blower number 3 tripped, also from loss of tightness. Now only 2 of the 4 critical blowers remained operational, and the reactor still contained over 1,000 megawatts of thermal energy that needed to be carried away. The reactor had been running at full power when the incident began. 1,492 megawatts thermal, 400 megawatts electrical. The CO2 coolant entering the reactor had been at 229 degrees Celsius, exiting at 402 degrees, a temperature difference that represented enormous energy transfer. But now, with half the blowers down and control systems failing, that heat wasn't being removed efficiently. CO2 temperatures began climbing, and so did pressure. The system was designed to operate at around 29.7 bar, but there were safety relief valves set to rupture at 30.1 bar. If pressure reached that threshold, membranes would blow, CO2 would vent, and the reactor would lose its primary coolant. The operators were now in a race. Keep the remaining blowers running, keep coolant circulating, keep pressure below 30.1 bar, or face the possibility of a complete loss of cooling. At 21:49, auxiliary electrical bus DS3A de-energized. Auxiliary group number 3 tripped offline. At 21:50, feed to principal heat exchanger cell number 3 was lost. The heat exchangers were critical. They transferred heat from the hot CO2 to water. That water boiled, made steam, drove the turbines. But more importantly right now, they removed decay heat from the reactor. Without all heat exchanger cells operational, the plant's ability to reject heat to the Mediterranean Sea was degraded. At 21:53, over-temperature alarms sounded on the gas, recirculator motors. The equipment was cooking. At 21:55, CO2 pressure in one of the measurement channels dropped to very low levels. Another auxiliary bus, DS4A, de-energized. Auxiliary group number 4 tripped. The remaining 2 blowers were increased to 700 revolutions per minute, pushing harder, trying to compensate, but the entire cooling architecture was fracturing, and then came the water. At 2200 hours, 10 p.m., the first indications appeared that water was accumulating in the reactor cavity. The reactor cavity was supposed to be dry. It housed sensitive equipment, cable penetrations, instrument lines, but demineralized water tanks were losing level. Water was being consumed uncontrollably, and it was flowing into spaces it should never reach. The sump pumps that would normally handle this had lost control power. They couldn't activate. Water began rising. By 23:30, 11:30 p.m., the water level in the cavity was confirmed to be affecting equipment. Estimates would later show that approximately 4,000 cubic meters of water flooded the plant. 4 million liters, enough to fill an Olympic swimming pool more than once and a half. An analysis would reveal something worse. 65% of that water was seawater, salt water, corrosive, conductive. Pouring into a reactor building filled with electrical equipment and hot surfaces. At the same time, CO2 temperature at the reactor ceiling hit 310 degrees Celsius, far above normal. Outlet temperatures from the remaining blowers exceeded 250 degrees. The pressure crept upward, approaching the relief threshold. If those safety membranes ruptured, the plant would face an entirely different emergency. The operators had no way to add more CO2. Once it vented, it was gone. And without coolant circulating, decay heat would concentrate in the fuel. Graphite temperatures would rise. At high enough temperatures, graphite can ignite in air, or react with steam. Vandellòs, I was teetering on the edge. Fire above, flood below. And inside the reactor, a slow climb toward conditions that could spiral into something far worse. At 2200 hours, the first fire brigades arrived. They came from Vandellòs, the newer pressurized water reactor next door, and from the nearby town of Hospitalet de l'Enfant. 53 firefighters in total. They had no special radiological equipment, no nuclear emergency training, just standard firefighting gear, and they were about to enter a burning nuclear facility that was simultaneously flooding. The operators had notified the CSN, Spain's Nuclear Safety Authority, at 22:11, 31 minutes after the fire started. That notification went to Salem, the National Emergency Operations Center, but by then the facility was already deep into cascading failures, and the people responding had no clear picture of what they were walking into. The fire was concentrated in the turbine hall, but smoke and heat were spreading. Cable trays ran throughout the conventional island. When insulation burns, it releases toxic fumes. Hydrogen was still leaking somewhere. Oil was still feeding the flames, and explosions were still occurring intermittently. The firefighters prioritized 2 objectives: extinguish the fire and pump out the water. Both tasks had to happen simultaneously, because the flooding was now as dangerous as the fire itself. Water was flowing through wall openings, passing into the irradiated fuel building, soaking motors, shorting electrical systems, The very equipment needed to maintain cooling was being drowned. Inside the control room, the operators faced an impossible puzzle. Half their instrumentation was unreliable or dead. Automatic controls were lost. Compressed air supply, used to operate pneumatic valves, was degrading. They were flying blind. And manually. At 2210, temperature defects were registered at CO2 blower outlets, above 250 degrees Celsius. The machinery was overheating. At 2213 and 2214, additional high-temperature indications appeared on the blower outlet measurement chains. The remaining two blowers, numbers 1 and 2, were being pushed beyond design limits. If either of them failed, the plant would lose all force circulation, and the reactor would be in free convection, passive cooling only, with decay, heat still pouring into a system that was leaking coolant and losing pressure control. At 2228, a new alarm. The spent fuel pool was showing a level defect. The pool held irradiated fuel assemblies, fuel that had been removed from the reactor but was still hot, still radioactive, and still required continuous cooling. The alarm was later attributed to water overflowing into a connected pit, but in the moment, the operators didn't know that. They had to assume the worst, that water was being lost from the pool, that fuel might be uncovered, because if spent fuel loses cooling, it can overheat. Zirconium cladding can ignite, releasing radioactive material. The operators had to monitor dozens of failing systems: CO2 pressure and temperature, blower status, heat exchanger flows, reactor cavity flooding, electrical bus status, spent fuel pool, all while working in manual mode, with incomplete information and a fire raging next door. At 2330, the water level in the reactor cavity was confirmed. Equipment was submerged. Motors that controlled critical pumps were soaked. Some were already damaged beyond immediate use. Engineers began identifying which components could be substituted, which backup systems still functioned. The plant had an alternative decay heat removal system, the RAY system. It could provide cooling through a different path, but it required electrical power and functional pumps, and those were exactly what the plant was losing. The operators improvised. They restored feed to one principal heat exchanger cell, then tried to balance flows across the degraded system. It was a manual, painstaking process, one valve at a time, one flow adjustment at a time, while CO2 temperature remained dangerously high and pressure continued climbing toward the relief threshold. At 0:20 on October 20th, 25 minutes past midnight, the operators managed to restore feed to principal heat exchanger cell number 1, 70 tons per hour of cooling water, a partial recovery. At 0:22 through 0:28, electrical buses DX3A and DX4A were re-energized. Power was slowly being restored, but low CO2 pressure alarms persisted across multiple measurement channels. The system was still bleeding coolant, still compromised. At 0:30 through 0:32, the pressure warnings continued. At 0:40, demineralized water production chains were recovered. At the same time, feed to heat exchanger cell number 2 was reduced to 10 tons per hour. The operators were carefully rebalancing the system. Too much flow in one area could starve another. They had to distribute cooling capacity across what remained functional. At 1:20 a.m., feed to cell number 1 was reduced to 20 tons per hour. Fine-tuning, stabilizing. The reactor's decay heat was slowly coming under control. At 1:30 a.m., the fire was declared controlled, not extinguished. Controlled, meaning it was no longer spreading, no longer producing explosions, but still burning in pockets. The firefighters had been working for 3.5 hours, in smoke, in heat, in a facility they didn't fully understand. They had no idea if they'd been exposed to radiation, no dosimeters, no protective clothing beyond their standard gear. They just fought the fire and pumped water, because someone had to. Dewatering began around 1:30 as well. Pumps that had been replaced or bypassed started moving thousands of litres out of the reactor cavity, out of the irradiated fuel building, out of equipment rooms, the seawater mixed with demineralized water, contaminated with sodium chloride, and carrying trace radioactive material from contact with contaminated surfaces. Later analysis would estimate the total activity in the purge collection pit water at approximately 1 millicurie. 1 millicurie equals 0.037 gigabecquerels. To put that in context, it's roughly 140 billion times smaller than the radioactive release from Chernobyl. It was a minuscule amount, contained entirely within the plant. But at 1:30 a.m., the operators didn't know that yet. They just knew they had radioactive water mixing with seawater, flooding critical areas, and they had to get it out. Between 1:30 and 3:30 a.m., the firefighters continued extinguishing hotspots, checking for reignition, ensuring the fire was truly out. Somewhere between 3:30 and 4 a.m. on October 20th, the fire was fully extinguished. 5.5 hours after it started, the operators kept 2 CO2 blowers running. Intermittent manual regulation, constant vigilance. The reactor was stable, but fragile. Any new failure could restart the crisis. The spent fuel pool cooling circuit had maintained temperature below 27 degrees Celsius throughout the event. 5 pool cooling pumps remained available after power restoration. The fuel in the pool was safe, but the facility itself was devastated. And then came the statements. On October 24th, Spain's Minister of Industry, Claudio Aranzadi, addressed the press. He stated that the fire had affected only the electrical area, that it was contained, that there was no radiological risk. The official line was clear. This was an industrial fire, not a nuclear emergency, but the people who had been inside knew differently. The operators who manually controlled a reactor on the edge of losing cooling, the firefighters who entered without radiological protection, the engineers who watched CO2 pressure climb toward the rupture threshold. They knew how close it had come, and the Spanish public was about to learn the truth, because the media had already started asking questions, and civil protection authorities, while confirming no off-site consequences, were beginning to acknowledge the severity. On October 26th, the CSN would call it the most serious nuclear incident in Spanish history. But by then, the narrative was already splitting, government officials downplaying, safety regulators warning, and the public beginning to realize that Vandellòs had nearly spiraled into something far worse. The 53 firefighters who entered Vandellòs 1 that night didn't know they were responding to a nuclear emergency. They knew there was a fire, they knew there were explosions, but nobody told them about the reactor flooding, or the CO2 system failing, or the pressure climbing toward rupture thresholds. They fought the fire, and then they went home. On October 24th, they were brought to Vandellòs II for radiological examinations. Every single firefighter tested negative for contamination. No radioactive material on their gear, no internal exposure. They had been extraordinarily lucky, because they'd been working in contaminated water, in smoke that had passed through areas with trace radioactivity, without dosimeters, without protective clothing, without any understanding of the radiological hazards around them. The official conclusion was clear. No harm done, but the question lingered. What if it had been worse? Spain in 1989 operated 9 nuclear reactors. Vandellòs was the oldest, and the most unusual. It had been authorized for construction on June 21, 1968. Initial startup was authorized on February 9, 1972. It entered commercial operation that same year. For 17 years it generated power, without major incident. A French design, gas-cooled, reliable by the standards of the time, but also aging. And unlike the 7 pressurized water reactors and 1 boiling water reactor operating elsewhere in Spain, it used a technology that was being phased out internationally, the UNGG design. It was cost-effective, but it had vulnerabilities. And on October 19, 1989, all of those vulnerabilities converged in 4 hours. The media began digging immediately, and what they found contradicted the official narrative. Minister Aranzadi had described the fire as an electrical problem, burned cables, nothing more. But journalists speaking to plant workers heard different stories. Flooding in the reactor cavity, loss of cooling control, explosions throughout the night, manual operation to prevent a pressure rupture. On October 26th, just 1 week after the fire, the CSN issued its own statement. They called Vandellòs the the most serious nuclear incident in Spanish history, not an electrical fire, a serious incident. The International Nuclear Event Scale, INES, would later classify it as Level 3, a serious incident. One step below an accident with local consequences, 2 steps below an accident with wider consequences, 3 steps below a major accident like Chernobyl, but still serious, still significant, still something that required investigation and accountability. The disconnect between the government's reassurances and the CSN's warnings created public distrust. People in Tarragona, the province where Vandellòs sat, began asking questions. How close had it come? What would have happened if the blowers had failed completely? What if the fire had reached the reactor building? What if the CO2 pressure had exceeded 30.1 bar? The official response was consistent. No radiological release to the exterior. Civil protection authorities confirmed no protective actions had been ordered. No evacuations, no sheltering in place, no distribution of iodine tablets, because there had been no off-site contamination. And that was true. Environmental monitoring showed no abnormal gamma radiation beyond the facility boundary. The 1 millicurie of activity detected in the purge collection pit water had never left the plant. But the public wasn't asking about what happened. They were asking about what could have happened. And that question was harder to answer, because the truth was uncomfortable. If the remaining 2 CO2 blowers had failed, decay heat removal would have relied entirely on passive convection and the RAE alternative system. If electrical power hadn't been restored when it was, the flooding would have disabled more equipment. If the fire had compromised more cable runs, control of critical systems would have been lost entirely. If CO2 pressure had reached 30.1 bar, the relief membranes would have ruptured, coolant would have vented, and the reactor would have faced a loss of coolant scenario. Each if was a branch point. Each branch led somewhere darker, and the operators had navigated through all of them, manually, in degraded conditions, with incomplete information. They had kept the reactor stable, but the margin between stability and catastrophe had been thin. Media outlets began using the word Chernobyl. Comparisons were inevitable. Chernobyl had happened just 3 years earlier, in 1986. It was fresh in public memory. The images of the destroyed reactor building, the evacuated cities, the radiation spreading across Europe, and now Spain had experienced its own nuclear fire, with flooding, with loss of control, with a reactor operating in manual mode for hours. The comparisons were inflammatory, and they were contested immediately. Official reports emphasized that Vandellòs was nothing like Chernobyl. Chernobyl released approximately 5.2 million terabecquerels of radioactive material. Vandellòs released effectively 0. Chernobyl's reactor core was destroyed. Vandellòs's reactor remained intact. Chernobyl required the evacuation of hundreds of thousands of people. Vandellòs didn't even activate off-site emergency plans. The scale was incomparable. But the fear was real. Forensic analysis began immediately. The CSN and independent experts descended on Vandellòs d'Abnome to reconstruct exactly what had gone wrong. The fire's origin was clear. Turbogenerator number 2 had developed abnormal vibrations. Those vibrations caused a lubricating oil line to rupture. Pressurized oil sprayed into the turbine hall. At the same time, the alternator's hydrogen cooling system developed a leak. The alternator was filled with hydrogen because it's an excellent coolant. But it's also explosively flammable. When oil, mist and hydrogen mixed in the presence of an ignition source, possibly from electrical arcing or hot surfaces, the fire ignited, and once it started, it spread. Cable trays throughout the turbine hall carried insulation that burned readily. The fire jumped from one tray to another. Each cable that burned took control circuits offline. The 48-volt DC control system was the plant's nervous system. It didn't carry power to major equipment, but it carried signals. Start commands, stop commands, position feedback, alarms. When those circuits burned, the operators lost the ability to control equipment remotely. They had to send people into the field, to manually operate valves, to manually start pumps, to physically check equipment status, all while smoke filled the building and water rose around their feet. The loss of control power to the sump pumps was particularly catastrophic. The sumps collected water from normal leakage, condensation, minor system drains. In normal operation, when water accumulated, pumps would activate automatically. But with control power lost, the pumps stayed off. Water accumulated. And because demineralized water systems were also malfunctioning, losing water uncontrollably, the volume increased rapidly. The demineralized water systems were designed to provide high-purity water for reactor operations, but they had failed in a cascading manner. The EDOR tanks began losing water. The EDOX and TF4 tanks showed uncontrolled consumption. Where was it going? Through pipe breaks, through wall penetrations, through any pathway into lower spaces, and 65% of the water that flooded the reactor cavity was seawater. That meant seawater cooling systems had also ruptured or leaked. Salt water was mixing with demineralized water, creating a corrosive, conductive slurry that shorted electrical equipment and damaged motors. The spent fuel pool level defect, flagged at 2228, was later traced to overflow into a connected pit. Not an actual loss of pool inventory, but in the moment, it added to the operator's burden. Another system to monitor, another potential failure to manage. The CO2 cooling system's degradation followed a predictable pattern. Loss of automatic control forced manual operation. Blower failures reduced circulation capacity. Loss of tightness allowed coolant to leak, and the fire's heat radiated into spaces where sensitive equipment operated. The CO2 blower motors began overheating, above 250 degrees Celsius. They were designed for much lower temperatures. Lubrication broke down. Bearings began to fail. When blowers 3 and 4 tripped, the remaining 2 blowers had to carry the full load. The operators increased their speed to 700 revolutions per minute, maximum sustainable output. If either of those final 2 blowers had failed, forced circulation would have ended, and the reactor would have transitioned to natural convection, which would have worked. Probably, but with degraded cooling water flow to the heat exchangers, uncertain CO2 leak rates and rising pressure, natural convection might not have been enough. The CO2 pressure approaching 30.1 bar was the single most dangerous moment of the night. At that threshold, safety relief membranes would rupture automatically. It wasn't optional. It was a physical barrier designed to prevent overpressurization of the reactor vessel. But once those membranes blew, the plant couldn't reseal them. CO2 would vent, the reactor would depressurize, and without coolant pressure, heat transfer efficiency would drop. The operators would be forced to rely entirely on whatever cooling paths remained functional, which, given the electrical failures and flooding, might not have been enough. They kept pressure below the threshold, barely, through manual adjustments, through careful balancing of blower speeds and heat exchanger flows, through sheer vigilance, but it was close, so close that the temperature at the reactor ceiling hit 310 degrees Celsius. The inlet and outlet temperatures of the CO2 had been 229 and 402 degrees at the start of the incident. Now they were spiking higher, outside normal operating bounds, in territory where materials behave unpredictably, where seals can fail, where structural integrity becomes uncertain. The operators held it together, but the margin was razor thin, and everyone involved knew it. The morning of October 20th, 1989 arrived with an eerie calm. The fire was out. The reactor was stable. CO2 circulation continued under manual control. But Vandellòs, the fire would never generate another watt of electricity. The facility had been operating for 17 years. It had weathered the oil crises of the 70s. It had provided power to Catalonia through Spain's transition to democracy. And now it sat silent, flooded, scorched, broken. The question wasn't whether it could be restarted. The question was whether it should be. Vandellòs I was owned by Hifrensa, a subsidiary of Endesa, Spain's dominant electric utility. Endesa was state-controlled, which meant the decision about Vandellòs's future wasn't just technical, it was political. Within days, engineers began assessing the damage. 4,000 cubic meters of seawater and demineralized water had flooded critical spaces. Electrical cables were destroyed throughout the turbine hall and parts of the reactor building. Motors were corroded, Control systems were compromised. 2 of 4 CO2 blowers had failed. Heat exchanger systems had been operating in degraded modes. The entire 48-volt DC control network needed rebuilding. It was extensive. It was expensive. And it would take time. The government faced a calculation. Option 1, repair and modernize. Bring Vandellòs way up to current safety standards. Replace damaged systems. Install redundant safety features. Upgrade emergency response capabilities. Estimated cost, 40,000 million pesetas, roughly $250 million. A staggering sum in 1989. Option 2, shut it down permanently. Decommission the facility. End Spain's experiment with gas-cooled reactor technology. Accept the economic loss, but eliminate the political risk. The choice seemed obvious on paper. Vandellòs I was Spain's only UNGG reactor. Every other operating reactor in the country was a light water design. Pressurized water reactors at Almaraz, Ascó, and Vandellòs the Heck. A boiling water reactor at Santa Maria de Garoña. Technologies with shared components, shared expertise, shared supply chains. Vandellòs. I stood alone. It used different fuel, different coolant, different operational procedures. It required specialized training, specialized parts, and specialized regulatory oversight. Keeping it running meant maintaining an entire parallel infrastructure. For a single 480-megawatt unit, the economics had always been marginal. Now they were impossible. But economics weren't driving the decision. Public pressure was. Within weeks of the fire, protests erupted in Naucilio, Tarragona. Environmental groups organized demonstrations. Local municipalities demanded answers. Citizens questioned whether any nuclear facility could be trusted, because the official narrative kept shifting. First, it was just burned cables. Then, it was a serious incident. Then it was INES Level 3. Then it was Spain's worst nuclear event ever. Each revision eroded confidence, and the comparisons to Chernobyl, however inaccurate, stuck in public consciousness. People didn't care that the radiological release was negligible. They cared that 53 firefighters had entered without protection. They cared that the reactor had been in manual control for hours. They cared that seawater had flooded the reactor cavity. They cared that nobody had been prepared for cascading failures. The political calculation became clear. Restarting Vandellòs I would require massive investment. It would require public acceptance, and it would require confidence that the same failures wouldn't recur. None of those conditions existed. On July 31st, 1990, 9 months after the fire, the Spanish government ordered Vandellòs 1 permanently shut down. Not temporarily offline for repairs, permanently. The reactor that had operated since 1972 was finished, and with it, Spain's use of gas-cooled reactor technology ended. The decision was framed as a safety measure, a prudent response to demonstrated vulnerabilities. But it was also a political necessity, because the government needed to show it was taking nuclear safety seriously, and the only way to do that was to end the controversy. Permanently. The shutdown order triggered a cascade of its own. Hifrenza, the plant operator, had to halt all operations, defuel the reactor, secure the spent fuel, begin planning for decommissioning. But decommissioning a nuclear reactor isn't simple, especially not a gas-cooled graphite-moderated design. The graphite moderator blocks were mildly radioactive. The reactor vessel's internal components were contaminated. The CO2 systems contained residual activity, and the fuel, hundreds of assemblies, needed to go somewhere. Spain didn't have a long-term repository for high-level radioactive waste. It still doesn't in 2025. So the spent fuel would have to be stored on site or shipped abroad, and either option required permits, infrastructure, and money. The international context mattered. 1989 was a watershed year for nuclear safety. Chernobyl's shadow loomed over every discussion. 3 Mile Island, the partial meltdown in Pennsylvania in 1979, had already demonstrated that Western reactor designs weren't immune to serious accidents. And now Vandellòs showed that even without core damage, cascading failures could push a facility to the brink. The International Atomic Energy Agency was expanding its peer review systems. The World Association of Nuclear Operators, WANO, was promoting information, Sharing and safety culture improvements. Spain's nuclear regulatory framework was being scrutinized, and Vandellòs' eye became a case study in what not to do: single-point failures, inadequate separation of safety systems, insufficient emergency preparedness, delayed communication with regulators, downplaying initial severity assessments. Every mistake was catalogued, every lesson was extracted, and the conclusion was consistent. Modern nuclear operations required defense in depth, redundant systems, independent safety trains, robust emergency response, transparent communication. Vandellòs, I had none of those. Spain's nuclear program continued. The 7 other reactors kept operating. New safety upgrades were mandated. Emergency planning was strengthened. Regulatory oversight intensified. But Vandellòs thought I was over. The facility entered a transitional phase. Staff levels were reduced. Operations focused on maintaining the spent fuel pool, securing radioactive materials, preventing further degradation, and preparing for the long process of dismantling. Because decommissioning a nuclear reactor can take decades, you can't just demolish it. You have to carefully dismantle contaminated systems, package radioactive waste, decontaminate structures, monitor radiation levels, and ensure nothing escapes into the environment. It's painstaking, it's expensive, and for Vandellòs, it had barely begun. But before decommissioning could advance, there was another question: accountability. Someone had to answer for what happened on October 19th, 1989. The dam near Mare had failed because of design flaws and cost-cutting. Vandellòs, I had nearly lost control because of inadequate safety systems and emergency preparedness. But who was responsible? The engineers who designed the plant in the 1960s, the regulators who approved it, the operators who ran it for 17 years, the company that maintained it, the government that licensed it. In May 1990, as the shutdown order was being finalized, prosecutors began asking those questions, and the answers would prove as complicated as the accident itself, because when a disaster requires a chain of failures, assigning blame becomes a legal puzzle, and legal puzzles can take years to solve, if they're ever solved at all. Vandellòs. I sat on the Mediterranean coast, quiet now, no longer generating power, no longer circulating carbon dioxide through a graphite core, but still radioactive, still dangerous, and still waiting for justice. In November 1999, 10 years after the fire, 8 managers from Hifrensa stood before a court in Tarragona. The charges were specific: failures in emergency planning, inadequate safety protocols, insufficient preparedness for cascading failures. The prosecution argued that the disaster had been preventable, that the company knew the plant's vulnerabilities, that they had operated for years without addressing fundamental design flaws, that when the fire erupted, there was no coherent emergency response, no radiological protection for firefighters, no timely notification of authorities, no contingency plans for simultaneous fire and flood. The 8 managers faced potential criminal liability, not for the fire itself, but for the failures that allowed it to spiral out of control. The defense strategy was straightforward: blame the design, not the operators. Vandellòs had been designed in the 1960s by French engineers, using French technology. The UNGG reactor concept was inherently complex. Gas cooling systems required extensive auxiliary support. The 48-volt DC control network was a single point of failure. The plant's layout allowed fire in the conventional island to affect reactor safety systems. These weren't operational failures, they were design deficiencies, embedded in the facility from day one, and the managers argued they had operated the plant according to all applicable regulations. They had conducted required inspections, they had maintained systems per manufacturer specifications, they had trained personnel to standard protocols. If the design was flawed, that wasn't their responsibility. That was the responsibility of the designers, the licensors, the regulators who approved it. The trial stretched across years. Witness testimony, technical analysis, expert opinions on what constituted reasonable industrial practice in 1989. The prosecution struggled to prove criminal negligence, because negligence requires demonstrating that the accused knew, or should have known, that their actions created unreasonable risk. But Vandellòs had operated for 17 years without major incident. It had passed regulatory inspections, It had met licensing requirements. Yes, the fire revealed vulnerabilities, but could the managers have reasonably foreseen that a lubricating oil line rupture would trigger hydrogen ignition, which would destroy control power, which would disable sump pumps, which would allow catastrophic flooding, which would threaten cooling systems? That chain of causation required hindsight, and the law doesn't punish people for not predicting the unpredictable. On October 23, 2003, 14 years after the fire, the Tarragona court issued its verdict. All 8 managers were acquitted. The court found insufficient evidence of criminal negligence. The fire had resulted from a combination of factors: equipment failure, design deficiencies, inadequate regulatory oversight, but not from deliberate misconduct or reckless disregard by the managers on trial. The ruling cited the plant's design flaws repeatedly: the lack of separation between the turbine hall and safety-critical systems, the vulnerability of the DC control network, the absence of redundant flood protection. These were architectural problems, not operational ones. And while someone might bear moral responsibility for those decisions, the law couldn't reach back to engineers and regulators from the 1960s and 70s. The statute of limitations had long expired. The responsible parties had retired or died, and the institutional memory of who decided what and why had faded. So no one was held criminally accountable for Vandellòs I. No fines, no prison sentences, no legal consequences beyond the shutdown order itself. The plant was dead, but the people who ran it walked away. It was a familiar pattern. Complex industrial disasters rarely produce satisfying legal outcomes, because when failures cascade through multiple systems and span decades of decisions, assigning blame to specific individuals becomes nearly impossible. The Baia Mare cyanide spill followed the same pattern. Romanian courts couldn't prove criminal negligence, because the dam failure resulted from design flaws, inadequate oversight, extreme weather, and operational compromises. Who do you prosecute? The engineers who built it, the regulators who approved it, the company executives who operated it, the government officials who licensed it? All of them? None of them? The legal system demands clear causation, but disasters don't work that way. While the criminal case crept through the courts, Vandellòs I's physical fate was already decided. On January 28, 1998, the Spanish government issued a dismantling authorization. Ownership of the facility transferred from Hifrensa to Enrisa, Spain's national radioactive waste management company. Enrisa was a state-owned entity created specifically to handle decommissioning and waste management. Because private companies don't want to own dead reactors, there's no profit in dismantling, only cost and liability. So the government takes over, socializes the expense, and begins the decades-long process of turning a nuclear power station into a greenfield site, or as close to greenfield as contaminated land can ever be. Decommissioning follows stages. Level 1. Immediate deactivation. Remove fuel, drain systems, secure radioactive materials. This happened quickly after the shutdown order. Level 2. Partial dismantling. Remove non-essential equipment, decontaminate accessible areas, package low-level radioactive waste. This began in 1998 and was completed on June 30, 2003, 15 years after the fire, but the most radioactive components, the reactor vessel, the graphite moderator, the primary circuit, remained in place. Because those couldn't be safely removed yet. The radiation levels were too high, the contamination too widespread. So Enrisa chose a different strategy: dormancy. On January 17, 2005, Spain's Nuclear Safety Council authorized a dormancy phase. The plan was simple: seal the reactor building, monitor it continuously, and wait. Radioactive decay follows predictable half-lives. Carbon-14 in the graphite has a half-life of 5,700 years, but most of the shorter-lived isotopes, cobalt-60, cesium-137, strontium-90, decay within decades. After 25 to 30 years of dormancy, radiation levels would drop significantly, making final dismantling safer and cheaper. So Vandellòs entered a waiting period, not abandoned, not forgotten, but frozen, a concrete tomb on the Mediterranean coast, waiting for isotopes to decay, waiting for radiation to diminish, waiting for the day when workers could safely enter and finish the job. But the spent fuel couldn't wait. Hundreds of irradiated fuel assemblies sat in the spent fuel pool. Still hot, still dangerously radioactive. They needed to be removed, and Spain had nowhere to put them. So the fuel went to France. Throughout the 1990s and 2000s, shipments of spent fuel left Vandellòs by rail, heading to Le Hague reprocessing facility in Normandy. At Le Hague, the fuel assemblies were dissolved in acid. Plutonium and uranium were separated and recovered for potential reuse. The remaining fission products, the truly high-level waste, were vitrified, turned into glass, sealed in stainless steel canisters, and stored. But France's reprocessing contracts included a provision. The waste returns to the country of origin. You send us your spent fuel, we extract the reusable material, and we send back the waste you can't escape. In 2023, France announced that processed waste from Vandellòs would return to Spain in 2028. The glass canisters, the vitrified fission products, everything that couldn't be reprocessed. Coming home, Spain would need to build a temporary storage facility on site at Vandellòs to house the returning waste until a permanent repository is built, and Spain still doesn't have a permanent repository. 35 years after the fire, the waste has no final destination, just temporary storage, indefinite temporary storage. In February 2025, the Spanish government opened the permitting process for that temporary storage facility, an interim waste store at Vandellòs, to hold the glass canisters returning from France, to hold whatever radioactive material remains from decommissioning, to hold decades of nuclear legacy in concrete and steel, until someone someday builds a place to put it forever. NRESA's current timeline projects final dismantling beginning around 2028 to 2030. 40 years after the fire, the dormancy phase will end. Radiation levels will have dropped enough to make the work feasible. Crews will enter the reactor building, dismantle the graphite core, remove the reactor vessel, decontaminate every surface, package every piece of radioactive material, and eventually, maybe by 2050 or 2060, the site will be released. No longer a nuclear facility, just land. But that's the best case scenario. Decommissioning timelines always stretch. Costs always exceed estimates. Technical challenges always emerge. Vandellòs, I might sit there for another 50 years. A concrete monument to a fire that lasted 4 hours, and to a technology that Spain used once and abandoned. No one died at Vandellòs. No one was injured by radiation. No contamination spread beyond the facility. By those measures, it was a success. But by every other measure, it was a failure. A failure of design, a failure of oversight, a failure of emergency preparedness, a failure to recognize that complex systems don't fail gracefully. They cascade, and once the cascade starts, stopping it requires luck as much as skill. On October 20th, 2024, 35 years after the fire, local authorities in Tarragona held a ceremony. They honored the 53 firefighters who had responded that night, the ones who entered without radiological protection, who fought flames they didn't understand, who pumped water from a reactor cavity they'd never been trained to recognize. The ceremony was quiet, a plaque, a few speeches, recognition that came 3.5 decades late, because in 1989 those firefighters weren't heroes. They were an embarrassment, evidence that Spain's nuclear emergency response was dangerously inadequate, evidence that when a crisis erupted, the people sent to fix it had no idea what they were walking into. But by 2024, enough time had passed. The fire had become history, the fear had faded, and the firefighters could finally be acknowledged, not for preventing a disaster, but for containing one. Vandellòs sits on the Mediterranean coast in the municipality of Vandellòs i l'Hospitalet de l'Infant, Bescamp Comarca, Tarragona Province, Catalonia. The geography matters, because the reactor was cooled by seawater, drawn directly from the Mediterranean, circulated through heat exchangers, and returned to the sea. That cooling architecture was both a strength and a vulnerability. It provided essentially unlimited heatsink capacity. The ocean doesn't run out, but it also meant that when systems failed and seawater flooded the plant, thousands of cubic meters of corrosive salt water invaded spaces designed for demineralized water only. The Mediterranean gave the reactor life, and on October 19th, 1989, it nearly drowned it. Spain's nuclear safety culture transformed after Vandellòs. The CSN, Consejo de Seguridad Nuclear, expanded its inspection authority. Emergency planning doctrine was completely rewritten. Every operating reactor had to demonstrate defense in depth. Multiple independent safety systems, backup power supplies physically separated, fire protection zones that couldn't allow cascading damage, flood barriers, radiological monitoring for all emergency responders, off-site emergency plans with clear communication protocols, and regular drills, not just tabletop exercises, full-scale simulations with firefighters, with local authorities, with the assumption that Murphy's Law applies, that whatever can go wrong will go wrong, and that the response must be ready for it. Internationally, Vandellòs became a case study. The International Atomic Energy Agency, IAEA, incorporated it into training programs. The World Association of Nuclear Operators, WANO, used it to demonstrate the importance of peer reviews. Because Vandellòs wasn't unique, it was just visible. Every nuclear facility operating in the 1980s had vulnerabilities. Single points of failure, design assumptions that seemed reasonable at the time but proved inadequate under stress, emergency plans that looked comprehensive on paper but had never been tested against real cascading failures. Vandellòs forced the industry to ask uncomfortable questions. Not, could this happen here? But, when this happens here, will we be ready? And the honest answer for most facilities was no. So the industry changed. Slowly, reluctantly, but it changed. The official record remains consistent. Vandellòs was an INES Level 3 incident. Serious, but not catastrophic. No radiological release to the exterior. No public health consequences. No environmental contamination. Civil protection authorities confirmed that no protective actions were ordered because none were needed. The 1 millicurie of activity detected in the purge collection pit water stayed inside the plant. The firefighters tested negative for contamination. Environmental gamma monitoring showed no abnormal readings. By every measurable standard, the containment held. The reactor remained under control. The fuel stayed cooled. The public was never in danger. Success. But that narrative requires accepting a very narrow definition of success. Success means nothing escaped, but it ignores how close everything came to escaping. Success means no one was hurt, but it ignores that 53 people entered a contaminated environment without protection. Success means the reactor stayed stable, but it ignores that stability depended on manual control, degraded systems, and operators improvising solutions in real time. Success means the legal system worked, but it ignores that no one was held accountable. Vandellòs, I succeeded the way a tightrope walker succeeds when they stumble but don't fall. Technically, they made it across. But everyone watching knows it could have ended differently. The unknown factors remain. Official reports never specified the precise maximum dose rates experienced by responders inside the plant during the event. They never calculated the exact mass of oil burned or the volume of hydrogen released. They never published detailed timelines of every manual intervention the operators performed. Some information was classified, some was simply never recorded, because during the crisis people were too busy keeping the reactor stable to document every action. And afterward, when it was time to write reports, some details had already been lost, memories fade, logs are incomplete, and institutions prefer tidy narratives to messy uncertainty. So, the official story is clean. Fire, flood, manual control, successful stabilization, permanent shutdown, decommissioning underway. But the people who were there remember differently. The operators who watched CO2 pressure creep toward 30.1 bar, the firefighters who entered without dosimeters, the engineers who calculated how close the blowers came to total failure. They know what the official reports don't say. that the margin between incident and accident was thinner than anyone admits, that if a few more systems had failed, if the remaining blowers had tripped, if electrical power hadn't been restored when it was, if the fire had lasted another hour, the outcome could have been catastrophic, not Chernobyl. Vandellòs' design wouldn't have allowed that kind of explosive release, but a loss of coolant scenario in a gas-cooled graphite reactor could have led to fuel damage, graphite oxidation, radiological release, and a very different conversation about nuclear safety in Spain. Today, Vandellòs remains in dormancy, a sealed concrete structure, guarded, monitored, waiting. In 2028, waste will return from France, vitrified fission products in steel canisters, the legacy of 17 years of operation, stored temporarily because Spain still has no permanent solution. Around 2030, final dismantling will begin. Crews will dismantle the reactor vessel, remove the graphite core, package everything radioactive, and by mid-century maybe, the site will be released. 70 years after construction began, 60 years after the fire, all to clean up 4 hours of cascading failures. Vandellòs is often called Spain's forgotten nuclear incident, because no one died, because nothing escaped, because it didn't become Chernobyl. But forgetting is easy when the disaster didn't happen, when the cascade stopped just short of catastrophe, when the operators held it together, when luck and skill combined in just the right proportions. The fire burned for 4 hours. The reactor will take 80 years to fully decommission, and the lessons about complex systems, cascading failures, and the brittleness of technology we assume is safe will outlast both. Vandellòs wasn't a disaster. It was a warning that every serious incident is a catastrophe that didn't quite happen, that every successful containment is a failure we managed to stop, and that the difference between the two is often nothing more than one more system failing. One more alarm ignored, one more decision delayed. The reactor is silent now, but the question remains, not whether Vandellòs was a success, but whether we've learned enough from that success to prevent the next failure, or whether we're still just one fire away from finding out what happens when the cascade doesn't. Stop when the blowers fail, when the pressure exceeds the threshold, when the operators can't improvise fast enough. Vandellòs held. The next one might not, and we'll only know which kind of incident we're facing when it's already too late to stop it. If stories like this matter to you, if you believe we need to remember these near misses to prevent the next disaster, hit subscribe and leave a like. Because the only thing more dangerous than a disaster is forgetting it almost happened.